It's a great pleasure and great honor for me to be a part of this course. So this is called Integrable Probabilities, and let me say first what this course will be about. So very roughly speaking, it will be about some class of probabilistic models which can be analyzed with the use of explicit formulas. So of course, this is just some class of models, and well, not every model can be analyzed with this method, but when we do have certain explicit formulas, we can obtain very delicate and very non-trivial results about their large time behavior. And also this class contains a lot of interesting examples of this class. The class of these models is quite rich. So we do know some very detailed results about some models, and also if we have some similar models which do not fall into this class, but well, a little bit similar to them, then we can make at least some predictions for some other models. So this is like very general philosophy and a little bit in more details. So there will be hopefully 8 lectures, 2 hours each. So this is a plan. Well, we'll see how it will go on. So this is a plan for these 8 lectures. So there will be 3 large parts. So in the first 3 lectures, I will talk about combinatorics of these models. So I will introduce symmetric functions, Schur processes, RSK algorithm. So this is basically the reason why this class of models that we will discuss, why we do have these explicit formulas for these models. The second part will be, so this is lectures 4 and 5, it will be about, large time behavior of this model. When we will have some large random object, and we will study this random object as a whole. So we will study some global limit regime. And in the third part, from lecture 6 to 8, we will study, so we will have some large random object, but we will look at it at microscope, and we will study how this random object behaves on the microscopic level. So this is one classification of what we will do. Another classification is, so first 2 lectures will be kind of introductory. So this is like, this material was probably well known 20 years or more before. Then lectures 6 and 7, so this will be about determinantal processes and how to show that Schur processes is a determinantal, and how to make an asymptotic analysis of Schur processes. So this was a development probably 10 or 15 years ago, approximately like this. And also some part of lecture 3, lectures 4 and 5, and lecture 8 will be about some more recent results. So it will be about results of, for example, like 5 years, last 5 years. So the main focus will be about tools, so how to analyze the system. But also, of course, it's nice to have some specific models where we can apply these tools. So in this course, we will not try to consider the most general examples. We will try to consider basic non-trivial examples. And well, so there is a certain choice which one we will discuss. So we will discuss 3 basic non-trivial examples where these techniques can be applied. So this is first example will be random tilings, domino tilings, rhombus tilings. Second example will be Schur processes. Well, of course, they do have an overlap, but still, so Schur process. And the third example will be a stochastic 6-vertex model. So this will be our 3 very specific models where we will see how all this machinery will be applied. But probably the main focus will be more on machinery rather than on these applications. Tools will be a little bit more general than just the results about these 3 specific examples. So this is what will happen in this course on this month. And probably now I can stop like this introduction and start with my very first example. And probably the most natural point to start is to consider domino tilings of the Alexey diamond. but probably, well, some questions at this point. Okay. So first two lectures, I said it will be just, well, quite introductory, and no recent results will be in the first two lectures. So let us start with Aztec diamond. So what is it, Aztec diamond? So of course, many of you already know this, but well, I need to introduce everything. So Aztec diamond is, roughly speaking, it's a square, but with sawtooth boundary. So the feature like this. We always have two cells adjacent at each corner of this square. And we will consider domino tiling of an Aztec diamond. So what is a domino? Well, domino is a rectangle 1 by 2. It can be either horizontal or vertical. And tiling means that we put dominoes on this Aztec diamond in such a way that they don't have overlaps and cover all our feature, all our Aztec diamond. So, well, it's not very hard to understand that we always have at least one tiling. For example, if we consider horizontal dominoes, well, we can cover. Or if we consider all vertical dominoes, well, this also gives us a domino tiling. But the question, how many domino tilings do we have, even for this feature, for this very specific Aztec diamond of size 3, it's not very trivial, and it's not even very easy to draw all these domino tilings in this case. So a little bit more formally, Aztec diamond of size n is a collection of lattice squares which are fully contained in the region absolute value of x plus absolute value of y is less than n plus 1. So absolute value of x plus absolute value of y is like a feature like this. So we have, it has some, it's a square. And we consider only lattice squares which are fully contained in this region. So we always obtain features something like this, but probably of a larger size. So the model of domino tilings of these regions were introduced by Elkis, Kuperberg, Larsen, and Probe. And they proved that the number of these tilings is equal to 2 to the power n times n plus 1 over 2, which we will also prove probably today or tomorrow. And well, as a first exercise, you can check that if we have Aztec diamond of size 2, then we have 8 domino tilings. So this is doable. Probably for size 3, it's already too many of them, but for size 2, it's possible to spend, I don't know, 30 seconds to write all these domino tilings. But our main interest will be not only, well, these combinatorial questions, so how many domino tilings do we have, but in probabilistic question. So how a uniformly random domino tiling of a large Aztec diamond looks like. So, yeah.
When you are cutting down, do you consider some?
So we consider all domino tilings. So we do not have any other constraints. So there are like quite a few of domino tilings that we can.
Two domino tilings can be the same if you just rotate.
No, we do not consider this symmetry. So just this like filaments of dominoes, and if we rotate, we consider them as different tilings. Yeah, thanks for the question. So please ask questions. I will greatly appreciate this. So these questions will be somehow probabilistic, so how this random object looks like, and this will be our main example, so our first example of this large random object that we want to study. So in order to show some picture, we actually will actually consider 4 types of dominoes. So it's quite clear that there are 2 types of dominoes, horizontal and vertical, but actually it makes perfect sense here to consider 4 types of dominoes. So we will consider chessboard coloring. So is it visible? Well, it's visible. So we consider chessboard coloring of Aztec diamond. And well, it's quite clear that each domino should cover 1 black cell and 1 white cell. And we will distinguish these 4 types of dominoes. So we will distinguish between these 2 types of dominoes and between those 2 types of dominoes. And on the next picture, we will color them by 4 different colors. So the question is how large uniformly random domino tilings for a large Aztec diamond looks like. So this is a simulation. It looks somehow like this. So in this picture, we color by four different shades of blue these four types of different domino tilings. And it's quite, so if you see this for the first time, it's probably quite, for me it was quite impressive that we have some, we clearly have some structure. So we pick a uniformly random domino tiling, but we definitely see some structure. So there is no probability happening here or here or here or here. So it's not some specific domino tilings. So almost all domino tilings of a large Aztec diamonds looks like this. And there is if we see this picture, we can ask, so what is happening here? So first question is, well, we probably see some circle here. So outside of the circle, we do not have any life. Everything is frozen. And inside the circle, we definitely see something else. So this is a theorem which was proved by Jokush, Prop, and Schur that this domino tilings becomes frozen outside of a certain explicit circle, which means that we have only dominoes of one type on each of the corners. So this is a phenomenon which happens for uniformly random domino tiling of Aztec diamond. But also we can ask, so this is like the most natural question, but we can also ask like a lot of more questions about this picture. So we can ask, so how it looks inside of the circle. So what can we say about the structure inside of the circle? And also we can ask like about some global asymptotics, or we can look at this picture at the microscope, for example, at this point, and try to understand how this large random domino tiling looks like when we look at it at microscope at this point. And all these questions are quite meaningful, and there are answers to these questions, and probably these questions will be also covered in this course. But they are quite non-trivial. So this is non-trivial objects. Even combinatorial part is not, so it's a certain result. So we will gradually answer to all these questions, and this will be probably the favorite example in this course. So all methods can be applied to this example, and we can obtain all the results using our methods. So this will be like a basic non-trivial example. Okay, so let us try to understand combinatorics of this picture. So we have domino tiling, so we have Aztec diamond, we have some domino tiling, and the first claim that I want to make is that I just want to pick two types of dominoes, forget about two other types of dominoes, so remove them from the Aztec diamond. So I tried to do this on this picture. So you see that this region is not covered by dominoes, and this region is not covered by dominoes. But I do have like dominoes of this type. So it's here, here, and here. And also the dominoes of this type, here and here, and also on the top. And so my question is whether I lost some information when I removed these dominoes or not. So it's written here that I didn't lose any information. So on this example, we see, so if we know the positions of these dominoes, so in how many ways we can cover this box? Well, there is only one domino which can cover this box. When we do have this domino, we can ask the same about this domino, then this domino, and also this feature can also be covered in a unique way. So at least on this example, we do see that domino tiling is uniquely determined by dominoes of two types. And this happens in the general case as well. So it's probably not reasonable to prove it in all details, but it works exactly in the same way. So let us move from northeast to south, from northwest to southeast. So first, let us look at these three boxes. So what can we say about these three boxes? So I fixed these two types of dominoes. Okay. That you know everything in advance. It's not fair. All right. So these three boxes can always, so they can be covered only by this. So either we pick this domino or this domino, it will be one of these two types. So we always know what dominoes cover these three boxes. So for this level, we know everything. So for this level. Then we move one step. On this level, we have 4 boxes, and 3 of them are already covered by dominoes from the previous step. And we have only one box left. And so for this one box, we can have like only one domino which can cover this box. So we know everything that happens on the second level. And we move this step by step for next level. So so on the first step, we have only one box. On the next step, we will have probably 2 boxes, 3 boxes. But well, when we draw these pictures, it will be also, well, it will be quite clear that there is only one domino which we can put into this box. So this like combinatorially moving from northwest to southeast, we recover the whole domino tiling by knowing just 2 types of dominoes. Yeah. So, but well, we need some. Well, we use some structure of domino tilings here. So, what do you mean by? So, I don't understand the claim, but which can be correct. Well, probably. Okay. Yeah. Okay. So I think it will be a general situation. So that. So I will try to just some basic examples. So, but that's true that many of these constructions can be analyzed and generalized to like much more probably interesting and general results. So as for bipartite graphs, I don't understand the statement, but. Okay, so for square lattice it's possible, but let us stick with these basic examples. Yeah.
Does this work also if you take the other vertical one?
Yeah. So this choice of 2 domino types is actually irrelevant. So we can just take any 2 types, and we will have the same statement. So probably I will need to move not from northwest to southeast, but somehow in this direction or in this direction. But other than this, nothing will change. I think so. But yeah, it will be another probably combinatorial statement. But so I will pick one horizontal and one vertical.
But if you take only horizontals, so you need to put only verticals, and you already know which to put because it depends.
Yeah. So the proof will be slightly different, but the statement that it determines is still correct. More questions? Okay, so this was first statement in this course, and well, it wasn't completely proved, but it was kind of proved, which will happen quite often in this course, at least in the introductory part. So let us move further. So we now fixed these 2 dominoes, the types of dominoes, and now I want to think about these domino tilings, not as like dominoes, but as about particle system. In order to do this, I will use these 2 domino types and put black particle in the black box of this domino and white particle into the white cell of this domino. So I use only these 2 types of dominoes that I fixed, and I do not put any particles on any other dominoes that I have in the domino tiling. So I already know that if I put particles in this way, so these particles completely determine domino tiling. So this particle completely determine dominoes of 2 types, and then these dominoes already determine the whole domino tiling. And my goal will be to forget about arc-stack diamond and dominant tilings of arc-stack diamond, and to think only about these black and white particles. So of course, if I just put some black and white particles randomly in the arc-stack diamond, it will not give a domino tiling. So for example, well, we need to have, so for each black particle, we need to have, well, some neighboring white particle. So, let us try to understand what positions of black and white particles will give rise to an actual domino tiling of an arc-stack diamond. So again, we will move along these levels. So if we look at these three boxes, we do know that they always have a white particle. Nothing is interesting here, so we don't even have this level. So we always have three white particles. We always do not have any particles in these three cells because we cannot cover it by these two types of dominoes. But we do have some life in between. We do have some choice for this first black particle. It can be in any of these four boxes. And then white particles should be either in this cell or in this cell, and then these constructions continue to go on, and we do obtain some constraints on black and white particles. And we will write these constraints in the following terms. So we look, we will encode the position of this black particle as an integer, also the position of this white particle as an integer, then position of these two particles as two integers. So the first claim is that we have on levels 1 and 2 we always have one particle, on levels 3 and 4 we always have two particles, and like on the levels 9 and 10 we always have how many? 5 particles. Again, so this is some combinatorics which is better just to prove by drawing pictures, and I will not, I'll just claim this, not actually prove. But we obtain this structure. So black particle, white particle, two black particles, two white particles, and so on. So now I will try to formulate the conditions on these sequences of integers. So one of notions that we will encounter on each lecture will be a notion of a signature of length n. So this is just a collection of non-increasing sequence of integers, lambda 1, lambda 2, lambda n. So we have n integers, and for some reason we call it a signature. Okay, so we can do this. Now I want some relations between signatures of two different lengths. If I have signature of length n and signature of length n minus 1, and I say that they interlace if, well, we have these inequalities. So we have 4 integers lambda, 3 integers mu, and they should interlace. They should be between each other. So this we should have these inequalities. And this situation will be denoted by mu less than lambda. I don't know how to read this symbol. So for example, 332 interlaces with 6320. And also we can draw the situation like on a picture. So 6320, I can write this as a Young diagram. So I can put 6. So there are different ways how to draw Young diagrams, and I assume that in Paris I should draw them in this way. 6 boxes will be in the bottom level, 3 boxes in the second level, 2 boxes, and then 0 boxes. This is 6, 3, 2, 0. And then 3, 3, 2 is... Everything is wrong. Yeah. Sorry for this. Yes, this is 3, 2, 2. Yeah. So this is 3, 2, and 2. So it should be anyway. So both of them interlace with 6, 3, 2, 0, which is good. This condition of interlacing means that this diagram should be fully contained in this larger diagram. And on the other hand, the difference between them should be quite small, and they should be what is called a horizontal strip. So we have these boxes in the set difference and this box, And no two boxes in this horizontal strip should be like in the same column. So this is what the condition of interlacing means, like in these geometric terms. So this is interlacing of signatures. That I also need a very similar notion of like vertical interlacing. So if two signatures of the same length, lambda and mu, differ by a vertical strip, so formally I will define this as like that every coordinate should be, so the difference between lambda I and mu I for any I should be either 0 or 1. And we have some example. So we again draw the signatures. And again, so this picture should be fully inside the larger picture of the larger signature, but the set difference between them should be a vertical strip, which means no two rows are in the same, no two cells are in the same row. So this is just some conditions on signatures, so whether they interlace or this like vertically interlace, or whether they differ by horizontal strip or by a vertical strip. So also it's quite clear that there is a certain symmetry, that if we make a symmetry with respect to x equals y, then these two notions go like if two signatures interlace, then we make the symmetry, and these two signatures will now vertically interlace. So hopefully these examples, are they the same? 3, 3, 1. 3, 3, 1. Yeah, so this example, so what is on the pictures, this corresponds to just taking this symmetry. Any questions? Okay. So one last thing that we will do with signatures is to make shift. So as I said, signature is a collection of n integers which can coincide. But now I can also, like it's very easy to transform, I can also consider a shifted signature, which means that I consider integers lambda I plus n minus I. So this is also n integers, but now they have to be distinct because I subtract this I. So even if they did coincide after this shift, I obtained distinct integers, distinct particles. So now I can finally state, so having this in mind, I can finally state what are the conditions on black and white particles in the Aztec diamond, in the domino tilings of the Aztec diamond. So it looks like this. So let us consider signatures with negative coordinates, which, well, so lambda I, mu I have length I, and we have this, well, quite complicated combinatorial constraint that lambda 1 is signature, well, just signature with one integer, then it should be vertically interlace with mu 1, then mu 1 should interlace with lambda 2, and so on. So this is like this structure of combinatorial constraints on the collection of signatures lambda 1, lambda 2, lambda n, mu 1, etc., mu n minus 1. So we can consider this object. We have some we have such signatures. It's not very hard to see that we have only like finitely many of these signatures because, well, we need to subtract vertical strips and add horizontal strips if we move from this direction. So this is like some finitely many signatures. And the statement is that we can understand domino tiling of the Aztec diamond only in terms of these signatures. So there are other ways how to understand domino tilings of Aztec diamonds, but this is one of possible choices, which is for Aztec diamond works quite easily. So let us try let us see how to prove this. Well, how this works in my favorite examples. So I have this feature, this domino tiling. So on each level, I have several distinct particles. So let me number this. So for example, for level 1, let me number this 0, 1, 2, 3. So I number each position by integer starting from 0. Then on the first level, I have particle position 1. Then on the second level, I have particle also, like this is 0, 1, 2. I have particle position 1 as well. Then here I have 0, 1, 2, 3. So I have particles at 1 and 3, and so on. So I just put positions of these particles. And now I make a shift back. So here I always, of course, have distinct integers. But if I want to write in terms of signatures, which I will want to do, I will make shifts and obtain 1, 1, 1, 2, 0, 1, 0, 0, 1, 0, 0, 0. So this is a collection of signatures, and at least, well, in this specific example, this collection of signatures does satisfy these combinatorial constraints of interlacing and vertical interlacing. Sorry? Yeah, so this is so these are these distinct particles, yeah. And if so from this making this shift, I obtain distinct particles. So I can do this stop in another direction that I will obtain signatures. So of course it's possible to formulate this interlacing for distinct integers, but well, we will see that for some reasons it will be more convenient to work always with signatures, to write everything in terms of signatures. So 1, 2 comes from this 1, 3. So so 1, 2 is a signature of length 2. So the shift is lambda 1 plus n minus 1. Yeah, so this 2 becomes 3, and this 1 becomes just 1. So from here to here is a shift, and from here to here it's like making inverse shift. It's equally easy. Yeah, exactly. So distinct, so I always like number distinct integers. Yeah, distinct. Yeah. So when I put this particle. So I put these particles, I put first like 1 and then 3. Yes, I always have like ordered collection of integers, and I just can have like strictly increasing collection for integers or weakly increasing collection for integers. So color does play a role because, well, so this is like for white particles, so they should be like from, and for black particles, they like in this position. So when they, well, yeah, so there is some structure here. So in this, at least in this example, this works. And of course, I will not prove this in general. So just, well, I have an exercise. You can check that, like just write in a couple of domino tilings of Ask diamond of size 3, just, well, to check to see that this construction works at least in the examples. And of course, the general claim is that this is a bijection. So when I construct from particles, I construct these collections of signatures. This is actually a bijection. And the proof is, well, just the same. So just moving from southeast to northwest, we check that what we can include, we exactly have this interlacing and vertical interlacing conditions. So this is possible to see. This is not very trivial, but it's possible to see, and this is just by, well, drawing pictures, and it's hard to check otherwise rather than drawing these pictures by yourself. So these particles, so we can now forget about domino tilings and think only about these particle systems which satisfy this admittedly not very easy combinatorial constraint. Any questions? So this is like some basic example. So where I think we can go to I don't know, to rare station and try to explain this, what's a diamond and dominoes, and probably there is a chance that it will go on smoothly. So this is like a quite basic thing, but it's non-trivial, and it will be a motivation to introduce some tools how to study these interlacing conditions and all this. So how to first to compute the number of signatures with such conditions, and then most importantly how to analyze what happens when these signatures becomes random. So the tools will be symmetric functions, Schur processes, which I will now try to introduce. So I run out of slides, so the rest of lectures will be a board talk. But so how to remove? How to?
I will do it.
Okay. So now I will spend probably the rest of this lecture and part of the next lecture talking about symmetric functions. So this is a very classical subject, which so many facts are due to great mathematicians of the end of 19th century and the beginning of 20th century. So Jacobi, Schur, Frobenius, Alfred Young, and probably Hermann Weyl, and many others. So as a source, probably one of the best sources is the book of Macdonald, Symmetric Functions and Whole Polynomials. Probably will mostly cover the material of chapter 1, first few paragraphs. But first I want to start with an easier object. I will just study symmetric polynomials. So sim n will be symmetric polynomials in x1, x2, xn. And this n will be large, but as for now, it will be just some fixed large number. So I will also need the notion of Young diagram, which was almost introduced on the slides. So it will also be denoted as lambda, and this is also some collection of non-increasing integers. There is small difference, quite annoying, but this difference exists, that these integers should be strictly greater than 0, and we have length of the Young diagram, L of lambda. I will denote the length of this Young diagram, and we can also, and we can and will think about Young diagram lambda also as a collection of, so also as a signature of length n. so a signature of length n, just by adding zeros to the end of this collection of integers. So if n is greater than L of lambda, then we can do this operation. And well, so it's a little bit annoying, but it's will be useful to remember this. So now let us try to understand what symmetric polynomials exist in variables x1, x2, xn. Well, probably first example which comes to mind, if we take just some monomial and symmetrize this monomial. Yeah, this is quite natural operation. So lambda will always mean signature of length n. So and if this is Young diagram, it is understood in this way. So n lambda by definition is the sum over beta 1, beta n x2 beta 2 xn beta n, where we sum over all distinct permutations of this initial Young diagram of lambda 1, lambda n. So let us do an example. M2, 1, 1 of x1, x2, x3. So what will be the answer? So what will be this function for signature 2, 1, 1 of length 3, 3? Sorry? Product times the sum. Okay. So if I will apply definition, then I will have these three terms. And well, of course, yes, we can write it as a product times the sum. But the point is that we sum only over distinct permutations. So I do not have coefficients 2 here. So well, this is just a definition. This is the most natural example of a symmetric polynomial. It's clear that these functions generate all symmetric polynomials if we are allowed to sum them. So this is called monomial polynomials. So there are some other examples and important families of functions. So first I will define this. So this is called elementary symmetric function. It is defined as a sum over indices I1, Ik. They are not allowed to coincide of variables x sub I1, x sub I2, x sub Ik. And then for arbitrary Young diagram lambda, it is defined as product of elementary symmetric functions for each of its components. So this is elementary symmetric functions. Okay, so any other ideas? So what can we also define here? Some natural families of symmetric functions. power sums. Okay, power sums, let's do power sums. Pk is the sum from 1 to n xi to the power k, and p lambda is also defined as p lambda 1 times p lambda L of lambda. So this is called Newton power sums. So it was Isaac Newton who first considered well, how these functions pk depend on ek and also on one more family, which is quite similar to elementary symmetric functions. But now I will allow equality here. So it is sum over indices which can coincide. xi1, xik, and also for arbitrary diagram lambda, it is defined as h lambda product h lambda 1, h lambda L of lambda. So this is called complete symmetric polynomials. So these are quite natural, so I think all four of them quite natural families of symmetric polynomials. But the most important for this course will be the next one, which is not that natural. So it is called Schur polynomial. It is defined in the following way. So if we have signature and variables, then Schur polynomial is defined as a ratio of two determinants, lambda j plus n minus j. So both of these determinants have size n. So this is determinants and variables x1, xn. But here, in the denominator we have Vandermonde determinant. So I will just write it as a product xi minus xj. Well, first of all, it's not that clear that this is a polynomial. This is a ratio of polynomials. But well, we can see that this is an antisymmetric function. So if we make a transposition of variables, we will get a sign. So all these polynomials are divided by Vandermonde. So this is a polynomial. Also, it is a symmetric polynomial because when we do this change, we have sign here and sign here. So we will obtain the same expression. So this is symmetric polynomial, which is less trivial than in the previous cases. Also, it will be nice to know what will be a degree of this symmetric polynomial. So degree will be, so we have this shift here, lambda j plus n minus j, but then we divide, and we can see that degree of Schur polynomial is lambda 1 plus lambda n, and this quantity I will denote as absolute value of lambda in this. So this object is quite non-trivial, and it is probably, well, main hero and one of the main heroes of these lectures. So any questions about this definition of this symmetric polynomial? So let us try to understand why do we need these Schur polynomials immediately, at least partially. So let us try to do something with this definition with determinants. So it probably can be called a proposition, because I will try to prove it. Proposition is that Schur polynomial in n variables can be written as a sum over signatures which interlace with lambda. So we already know that we are interested in interlacing, and we will now see how this appears in Schur functions. So this is a certain statement about Schur polynomials. I consider the variable xn separately, and I'm interested in what a coefficient for each power of xn. And it turns out that it can be written as a sum over signatures mu, which interlace with lambda. So mu is a signature of length n minus 1. We already know what does it mean interlacing. And, well, this is a claim that this interlacing naturally appears for Schur functions, Schur polynomials. So let me try to prove this. First, I want to plug 1 as the last variable, xn minus 1, and then I will put 1 here. Well, the only thing that I know is a definition, so I need to write these large determinants. This is a determinant x1 lambda 1 plus n minus 1 x1 to the power lambda n, then x n minus 1 lambda 1 plus n minus 1 xn minus 1 lambda n. So then I put 1, so I have 1, 1, 1. So this is first determinant, and second I have product of xi minus xj to the power minus 1 and I also have 1 over x1 minus 1 xn minus 1 minus 1. Oof. So I just applied the definition and put 1 instead of the last variable. Now I want to see, well, this structure, so I already write an answer. So what can we do? So how can we try to prove this equality? So what should we do? Well, expand the determinant. We will obtain some large determinants. So I suggest to transform a little bit this determinant before expanding.
Sorry, the product should go with J up to n-1.
Yeah, thank you, thank you. Of course, this was intentional to check. Thank you. Please correct my other intentional mistakes as well. Okay, so so I suggest to do something with this determinant. And if we have ones, then expanding is easier than if we have a lot of zeros here. So probably we need to try to subtract these rows. Okay, I will continue this equality. So I will do the following transform. So I will subtract second row from the first row third row from the second row, and etc. Nth row from the n minus first row. And I will obtain determinant. So this transforms will not change determinant. So here I will have x1 lambda 1 plus n minus 1 minus x1 lambda 2 plus n minus 2, because I subtracted second row. Here I will have x1 lambda 2 plus n minus 2 minus x1 lambda 3 plus n minus 3. So last row will not change. But second to the last will be x1 lambda n minus 1 plus 1 minus x1 to the power lambda n. So then I will have n minus 1 of these columns. I will not write like this column, but it will have the same structure with x1 replaced by x sub n minus 1. And on the last column, I will have 0, 0, 0, 0, and then 1. So I have these terms, and I also have like unnecessary these terms, which I want to use somewhere in the determinant, because I need this term for Schur functions. But this term I can use, so I will not write large determinants, but I will just say that xa to the power a minus x to the power b over x minus 1. This is a sum over integer c such that b is less than equal to c less than a, x to the power c. So I have difference of two powers of x1, and if I divided this by x1 minus 1, I can write it as a sum of x1 to some powers. This will be a sum of powers of x1 so applying, okay, I will not write equalities. So applying this expansion to each box in this determinant, I will obtain determinant with sums in all these boxes. And then this, I will divide it by Vandermonde in n minus 1 variables. And this is exactly this sum. So if I write this sum of Schur functions as a sum of determinants and look at definitions, I exactly obtain, so interlacing appear because I have all integers here. So all integers here are between these two numbers. And this will be exactly the sum that I have here. So I will not write like more large determinants, but it's quite clear even without writing that I will obtain exactly this. With interlacing appear because of this condition. So
this is not strict, one inequality is strict, but then there is an n minus 2, for example, instead of n minus 1.
Yeah, exactly. So this is strict, but it is for shifted coordinates. So when I make this shift back, I will obtain exactly interlacing. So from this, I proved that S lambda x1 xn minus 1 1 is a sum of that's mu. But now, now I want to have this equality which includes xn. But for this, I can just say that I know the degree of Schur polynomial. So if degree of this guy is sum of lambdas and degree of this guy is sum of mu's, then xn should appear in the power sum of lambdas minus sum of mu's. So I can conclude the proof here. So from this equality, this one is immediate because we know the degree of a Schur polynomial. So, okay, so we proved, well, quite a non-trivial thing for Schur polynomials. Let us make some corollaries. So if I did one step, I can make all other steps and write this polynomial as a sum of like xn, put here xn minus 1, and so on. So what I will obtain is called combinatorial formula for Schur polynomials for S lambda x1 xn is the sum, large sum, lambda 1, lambda 2, lambda n equals lambda. So I can see, okay, so it's a sum over lambda 1. So I will explain this lambda n minus 1 such that we have this interlacing. And here I should write x1 lambda 1, x2 lambda 2 minus lambda 1, xn lambda n, which is fixed, minus lambda n minus 1. So I obtained this formula just by applying this statement for this Schur polynomial, then for the Schur polynomials that are obtained after this, and so on. So I obtain some combinatorial structure. So I start with some fixed signature lambda n, which equals to lambda. Then from the first step, when I separate first variable, I obtain some interlacing signature, lambda n minus 1. And I need to sum over this lambda n minus 1 because, well, I do have a sum here. Then when I do the same step for xn minus 1, I obtain the next level, lambda n minus 2. And I have interlacing between these two levels. So I do not have any non-trivial, well, any trivial condition between this level and this level, but I do have interlacing here and I do have interlacing here. And so on. In the end, I will end up with one signature of length 1, it will be lambda 1. So this is a combinatorial formula for Schur functions with sum over all interlacing arrays with fixed top row. So in this, for this definition, it's quite clear that this is a polynomial. I don't have any division here. But for example, it's not very clear that this is a symmetric polynomial. So notice that x1 is in this degree and xn minus 1 is in this degree, well, it should be symmetric. It's, from this definition, it's not entirely trivial. So of course it's possible to prove just looking at this expression, looking what is going on, and it's possible to prove that this is symmetric, but this is not trivial from the definition. So we have two different definitions of a Schur function. Now, well, this also can be considered as a definition from determinants and from combinatorial formula. And this will be like essential thing for this course, because combinatorial formula gives us some interesting non-trivial combinatorial object, this interlacing arrays, and determinant formula gives us ways how to analyze this combinatorial object. So actually there is like at least one more very important phase of Schur functions, and this is that the Schur function is a character of irreducible representation of a general linear or unitary group, and like this is a phase of Schur function will lead us very close to the course of Philippe Bian, but this will not be like covered in details in this course. So for this course, for us it will be important the connection between these determinants and this combinatorial formula for Schur functions, or for Schur well, as for now, for Schur polynomials. Well, probably it's reasonable to make some examples. So let us compute some Schur functions. For example, if I want to understand what is a Schur function on signature of, so just K. So how to compute Schur function? Yes, yes, it's a good hint. Okay, so I wrote, okay, example. Okay, so this is a complete, symmetric polynomial. Well, just use this combinatorial formula, see what does it mean, and it will be exactly the definition of a complete symmetric polynomial. So okay, so now S1, 1, 1, K, x1, xn. Any guesses? Elementary, yes. So it will be elementary symmetric polynomial. So this is example and exercises, okay. So example and exercise. For example, something like S21 of x1, x2. Okay, so let me do something and compute S21. So 21, I need to fix. So in order to compute this, I need to fix 1 and 2, and to sum over all interlacing arrays, which has 1 and 2 as a top row. Fortunately, I have only 2 of them, 1 and 1, 2, 2. And this will be, when I do this, so it will be x1, x2 squared plus x1 squared x2. So at least for small Young diagrams, for small signatures, we can compute this function using combinatorial formula. It's easier to feel what is this symmetric polynomial is about. Of course, the computer will compute like by using determinants as well. It will be quite fast. But well, both these formulas will be very important for us. Also, I probably want to state somewhere here that from combinatorial formula we have stability property xn 0 is equal to S lambda x1, x2, xn. And so this will be important for me a little bit later. Stability. So these are some combinatorial, these are some corollaries of combinatorial formula for Schur polynomials. Any questions? Well, this is also like some, I think, corollary from this formula or from determinants. I also think it's visible, yeah. But
yeah. Over there you can see that the numbers are the interlacing.
Yeah, just interlacing. So this is a shift of this picture in some direction. Yeah, it's probably more visible. Yeah, thank you. Okay, so we already saw interlacing like horizontal strips. But in Aztec diamond, we also saw that we need vertical strips. And it's not here. So let us formulate something which contains vertical strips. It will also be proposition. I will try to prove that product of Schur function times, so we can multiply polynomials, times elementary symmetric function is the sum over all okay, let me write it in order to be consistent. Let me write here Schur function as mu. And here I will sum over all lambda such that lambda minus mu is a vertical strip. So I already defined what does it mean for a set difference of two Young diagrams to be a vertical strip. That means that two boxes cannot be in the same row. And here I should write as lambda x1, x2, xn. So this is about how to multiply a Schur function and elementary symmetric function. So this is called probably Pierre's rule. One of its versions. Vertical strip, it's one. It is yes, it's like with K boxes. Thank you.
Possibly disconnect.
Yeah, so there was example like in the beginning. So yeah, so this is two Young diagrams, but the set difference between them is something disconnected, and the only condition is that it doesn't contain two boxes in the same rows, and of course, and it should be exactly K boxes. Yeah, thank you. So let me try to prove this at least to a certain extent. So again, for proving things, I will use determinant definition. So this determinant comes from, oh, I need to use mu's. OK, I need to use mu's. Sorry for this. Here I want to multiply by elementary symmetric functions. I have only definitions. Well, I also have a Vandermonde, but well, I didn't write it. So I need to multiply this determinant, essential determinant from Schur functions, and elementary symmetric function. I will do this just by definition of determinant. Also, I put this summation first. So determinant, as far as I remember, is the sum of all permutation of symmetric group of size n. I need to write sine of sigma, then x1. Here I need to write something awful. Mu sigma of 1 plus n minus sigma of 1 xn mu of sigma of n plus n minus sigma of n. Yeah, I'm sorry for this computation, but well, I feel that I need to prove something in this course, so I'm trying to do this. And also, I need to multiply, well, I can put it here. And this for xi1, xi2, xik. So this is a large sum over indices I and also over all permutations of, well, which comes from this determinant. And this large sum I can write as a sum of determinants, also quite large. Such that, okay, I will first write it and then so basically these additional terms will exactly add boxes into the diagram. So we need to add k boxes, and they will be exactly added at positions I1, I2, Ik. And well, this is basically the whole proof. So, but I will write one more sum in order to be precise. So I need to sum of all indices, which can be 0 or 1, and the sum over all indices is exactly k. And here I will have a determinant of almost the same thing, but x1 mu1 plus n minus 1 plus I hat 1 xn is 1 lambda, not lambda, mu mu n plus So I hope this is a last large determinant that I will write. Mu n plus hat n. I hope that something like this is correct. So what is happening here? So first I just expand. This is a large sum over indices I and over permutation. And there I just notice that this is just a sum of determinants. So these new factors can be, can just appear here. So here I sum over all indices like hat I1, hat IN. So each of these indices is either 0 or 1, and their sum is equal to k. So this is just k rows where I can add these boxes. And I have this determinant, which is exactly what I will have here, because when I divide by van der Waals, I obtain Schur function. So the only thing that I should notice is that if this is not a vertical strip, so I add some boxes to some rows, and if it turns out to be not a vertical strip, then this determinant will be 0. So these terms will disappear, and all other terms will give me these Schur polynomials. Well, it's probably a little bit complicated. Well, this is just some formal equality, and after some looking, it will be clear if needed, or you can just believe me that this is true.
There is a shortcut, but maybe if you sum over k z to the power k on both sides, the ek becomes a product of 1 plus z xi, which you can follow without expansion.
Yeah, of course, there are different ways to see this. This is not the only one. Well, at least it's relatively short. So this is one more manipulation with determinants, which gives us a condition of this like vertical interlacing. So now I'm finally able to count the number of domino tilings of Aztec diamond if there will be no, so if probably some questions before this. So we have interlacing horizontal strips, we have interlacing vertical strips, and it will give us the number of domino tilings. So let me prove this. So proposition, number of domino tilings Aztec diamond is 2 to the power n plus 1 over 2. Or equivalently, as we kind of see that the number of signatures lambda 1 mu 1 mu n minus 1 lambda n such that lambda 1 is less than mu 1. Oops, no. It's vertically interlaces with mu 1. Lambda 2 vertically with mu 2.
And you really have to put a 0.
Well, I can put 0 here for symmetry. It's not. No, I claim that. So I want to say that lambda I and mu I has length I. It's like. It's not important. So mu n minus 1 lambda n. Okay. So I have this condition, and also, so actually it's not very important, but I will also, just for clarity, say that lambda I mu I has length. So number of signatures with this condition is equal to two to the power n plus 1 over 2. Well, so I did all these computations, and I defined all these propositions, and in order to use them, so let me try to use them. So I need to start with 2 to the power n plus 1 over 2. Then I want to write this wonderful number as a product 1 plus xi, I from 1 to n. There should be some power, probably n minus I plus 1. And then x1 equals 1. Okay, I'll write it in the form x1, xi equals 1, I from I1 to n. So this is probably, will look as some machination, but this is not. So this is quite a reasonable way to compute the number of domino tilings. But as for now, this will look a little bit as a trick which uses these statements about Schur functions. So I write the following not very intuitive thing. So I write 1 plus xi to the power n minus I plus 1. So this is, it's probably easier to think about this as 1 plus x1 to the power n, 1 plus x2 to the power n minus 1, 1 plus xn to the power of 1. So I hope this is the same things. And then I plug all this xi equals to 1. So this is actually just 2. And 2 is raised to the power n minus 1, etc. 1. So the sum is exactly n times n plus 1 over 2. So this is correct equalities for now. And no Schur functions. Now Schur functions will appear. And the first step, I will take one factor from each of these things. I will want to write 1 plus x1, 1 plus x2, 1 plus xn in terms of Schur functions. So what will be my answer if I want to write this product as a sum of Schur functions? Okay, that's true. sum from k from 0 to n elementary functions and this is a sum, as we mentioned, sum of Schur functions at 1, 1, 1, k, x1, x2, xn. So that's how Schur functions will appear in the first place. So this product of 1 plus x1, 1 plus x2, 1 plus xn can be written as the sum of Schur functions. So I will do this transform here. So I do not touch product from 1 to n minus 1, 1 plus xi. So I just take one factor, so it will be n minus I. So this is like what remains, but I took one factor from, so I took this product 1 plus x1, 1 plus x2, etc., and wrote it in terms of Schur functions. So this sum as 1, 1, sum from k. Okay, I don't want to have this k. I will write this as lambda n, which vertically interlace 0. And this 1, 1, 1, 1, I will also write as lambda n. Anyway, it should be just a vertical strip. So this is x1, x2, xn. And I always have these evaluations of all functions at 1. So I always have this just this number 2 to the power n times 10 plus 1 over 2. Okay, so this was the first step where I used, this statement applied to, so I will use this statement. I used this like simple version of this statement, which is this expansion into elementary symmetric function. Now I need to plug 1. I want to do this only for this variable x1 for the last variable. And I know how it looks like for the Schur function. So this strange factor in the beginning will remain from 1 to n minus 1, 1 plus xi, n minus I. All evaluations and in this variable it's x1, xi equals 1, I from 1 to n minus 1. But here, if I will apply to this Schur function evaluation for the last variable at 1, I will obtain another sum. I will obtain the sum over mu n minus 1, which is interlacing with lambda n, which is vertically interlaces with 0. As mu of n minus 1, x1, xn minus 1. And I also should evaluate this at all ones. So I make two steps. This is basically this step, and the previous step was plugging 1 into Schur function. And I obtained first two signatures, the sum of mu's and lambdas, which I have here with exactly the same conditions. So now we will do just this, we will repeat these steps. So I will write 1 plus x1, 1 plus xn minus 1 as a sum over elementary symmetric functions x1, xn minus 1. So in the next step, I will again take this factor, but will just n minus 1 variables multiplied by these Schur functions using this formula, and I will obtain the next step in this sequence, which is vertical interlacing here. So when we know this like non-trivial properties of Schur functions, this is somehow works automatically using this step. So any questions at this point? So what we are doing and why does it work? Yep.
How can we continue this?
Okay, so how?
Sure, the lambda, well, the next one.
Okay, so let me try to write here next step. So product, so I from 1 to n minus 2. So I again take one factor from each, 1 plus xi to the power n minus I minus 1 times, I use this thing, so this is sum over ek. So I will not write indices x1, xn minus 1 times this large sum of Schur functions s mu n minus 1. So I have this sum of elementary symmetric functions and the sum of the Schur functions. And I just multiply this ek to each of these Schur functions using this property. And this will give me this vertical interlacing. And it will be exactly the sum of Schur functions over triples of signatures over this signature, and over this signature, third one. So just expanding, 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 and in the end, I will obtain, well, I need to write it somewhere. So in the end, I will obtain
Is there a straightforward
Oh,
Q
sorry.
version of this?
Q version.
Putting in Q to practice some statistics on it. Like maybe you start-
Yeah, so it's called probably one periodic hard-stack diamond if you put like Q to horizontal ones, for example. And its partition function can be computed in the same way exactly.
Is there a cyclic Savin or anything like that?
So there are many generalizations. So probably we can discuss it after this. So I'm just not sure. So I'm sure in the following fact that if you put on horizontal tiling, you put weight Q, then it can be computed, and yes, it is computed exactly by the same way. And we can discuss this a little bit more after the lecture. Yeah. So I have questions. Yeah. So I need to write last. Sum over ones, a sum of ones over all lambda I mu I, such that empty set lambda 1 mu 1 vertical mu n minus 1 lambda n vertical zeros, and this is exactly number of domino tilings. Of hard-stack diamond. So this is not, so of course there are other different proofs of these propositions of this combinatorial statement about number of domino tilings, and I do not claim that this is the best one. Of course this is not true, but this is reasonable, and it allows us to introduce some notions, most importantly Schur polynomials, that will be used also for probabilistic analysis of uniformly random domino tiling. So I still have some time. So let me move further. So this was like the main goal of this lecture, to prove this combinatorial statement. But our next and more important goal is to understand uniformly random domino tiling. So we need to introduce some object which covers this situation. So we have this condition on signatures, and we need some object how to think about this object in terms of Schur functions and probabilistic terms. So our first attempt to do so will be the notion of like Schur. I need, So I need a little bit, I need to state some facts. So fact which will later become proposition, because I will prove it probably on the next lecture. So it's this Cauchy identity. So the claim is that the sum over all lambdas as lambda x1, xn, as lambda y1, yn is actually is a product of 1 over 1 minus xy yj I from 1 to n and j from 1 to n. So here we have a sum over all Young diagrams. So this will be a set of all Young diagrams. So when we see this object, so one way to think about it probabilistically is to define, so this is a definition of Schur measure. First version. So first, for like the purposes of this talk, of this course. So the notion of Schur measure is due to Okounkov. So this is a probability measure on the set of all Young diagrams such that probability of Young diagram lambda is determined by, basically by this Cauchy identity. So we have parameters, let us say A1, AN, B1, Bn, positive reals. we need to take this product over 1 minus AI bj as lambda a1 an as lambda b1 b1. Well, it's probably nothing is visible here, but anyway, so we have some combinatorial identity for Schur functions, and now this can be interpreted as a sum of a large amount of terms, so that the large sum is equal to 1. And this can be thought as, we can think about this as a definition of probability measure. If each of these terms is non-negative, we can just assign to each diagram lambda a weight, which in this case will be the product of these two Schur functions times, well, this normalizing constant. Yeah.
For each pair of sequences, A1, AN, B1, BN, we have
so this is parameters. So for each, if we take these parameters, we can define this measure. So these Schur functions will be positive because we have combinatorial formula. So this is a sum of positive terms. So this will be some positive real. This will be some positive real. So it also So this thing should be positive. So AI times bj should be less than 1. So this thing should be also positive. And other than that, we have no other constraints. This is a Schur measure with parameters AI and bj. So why do we need this? It turns out that this object is very close to this one. So here we recall that our goal is to consider random signatures of this form and to understand something. So let us say, for example, for signature lambda n over 2. So for some signature which lives in the middle of this sequence. We cannot say, for now, we cannot say anything about it, so how uniformly random signature looks like. And it turns out that this distribution on these signatures will be very close to this Schur measure. But it will not be the same. It's not exactly this. And the reason for this is that we have both horizontal so we have like horizontal interrelation and vertical interrelations, horizontal strips and vertical strips. And this definition captures only horizontal strips. So this is quite close, but not exactly the distribution of lambda n. So we will have like a more general definition of Schur measure, which will look almost like this, which will cover the distribution of lambda n. But for this, we need to build the theory of symmetric functions. So as for now, I had only symmetric polynomials in n variables. So as for now, it was symmetric polynomials n, x1, xn. And I want to consider polynomials in x1, x2, x3, etc. in infinite amount of variables. It will be almost the same polynomials because I will want to consider them of bounded degree. So it will be essentially the same polynomials, but still the structure of these symmetric functions, this infinite amount of variables, will allow us to capture this vertical interlacing in a formal way. And I think we will see this on the next lecture, because now is quite a good time, I think, to finish this lecture. And next lecture, I will give also some facts about symmetric functions, not only symmetric polynomials. We will have definition of Schur measure and Schur process. So it will be like truly probabilistic objects. And also we will start to discuss how to sample Schur measure and Schur process by using RSK algorithm, which is like another well-established combinatorial topic.